Q264. Discuss the supporting evidence, as well as the counter-arguments against Alfred Wegener's theory of continental drift. 15 marks, 250 words, core demand of question. Discuss the supporting evidence for Wegener's theory. Shed light upon the counter-arguments against Wegener's theory. ANS. Alfred Wegener's theory of continental drift proposed that Earth's continents were once part of a single supercontinent, Pangaea, which gradually drifted apart over millions of years to form the present-day arrangement of continents. While Wegener's theory laid the foundation for modern plate tectonics, it faced both supporting evidence and counter-arguments during its early reception. Supporting evidence for Wegener's theory. Jigsaw fit. One of the prominent pieces of evidence supporting the theory of continental drift is the striking resemblance in the coastlines of continents. For example, the coastlines of Western Africa and Eastern South America align in a way that they appear to fit together like pieces of a jigsaw puzzle. Fossil distribution. Similar fossils found on continents now separated by oceans indicate a shared biological history. For example, as a case in point, the presence of fossils of lemurs in India, Madagascar, and Africa suggests the connection of these landmasses in history. Glacial evidence. The presence of glacial deposits and striations in regions not near modern-day polar areas implies a different arrangement of continents. For example, the alignment of glacial striations in South America, Africa, India, and Australia indicates that these continents were once joined and covered by a single ice sheet. Coal beds. The existence of coal formations in regions such as Antarctica and India serves as compelling evidence that these currently distant areas were once geographically closer and experienced similar environmental conditions, thus supporting the concept of drifting landmasses. Placer deposits. Placer deposits of gold found along the coast of Ghana in West Africa are notable examples. These deposits lack a local source rock in the region. For example, the occurrence of these deposits can be explained by the fact that when South America and Africa were adjacent as part of the supercontinent Pangaea, the gold-rich region of Brazil was in close proximity to West Africa, leading to the transport of gold deposits through water currents. Mountain range alignment. The alignment of mountain ranges across different continents supports the idea of continental drift. For example, the Appalachian Mountains in North America and the Caledonian Mountains in Scotland share similar geological features, suggesting that they were once part of the same continuous mountain chain. Counter-arguments against Wegener's theory. Driving factors. Forces provided by Wegener, i.e., the differential gravitational force and the force of buoyancy and tidal force of the Sun and the Moon are insufficient to drift the large continents. Contrasting viewpoints of Wegener. Initially, Wegener described Sial as freely floating mass over Sima, without any frictional force of Sima, but later, he described forceful resistance by Sima to the free movement of Sial to explain the origin of mountains along the frontal edges of floating continents. Difficulty in gaining evidence. It is difficult to show the crumpling of Sial blocks at their frontal edges and formation of mountains during their passage through the Sima. Invalidation of jigsaw fit. By the coasts of the Atlantic Ocean which cannot be completely refitted. Direction and chronological sequence. Wegener did not explain the direction and chronological sequence of the continental drift. Limitation of geological time frame. Wegener did not describe the situations before Carboniferous times. Alternative explanations. Some scientists proposed alternate explanations for the observed similarities, such as parallel evolution. For example, similar fossils and rock formations could be attributed to convergent evolution or random geological coincidences. However, plate tectonics later provided a more comprehensive framework to explain these observations. Lack of geological expertise. Some critics raised concerns about Wegener's background in meteorology and his limited geological expertise. They argued that a theory with such profound geological implications should be developed by someone with a stronger geological foundation. The theory of continental drift, despite navigating through the realms of supporting evidence and counter-arguments, stands as a pivotal milestone in our understanding of Earth's geological history and the arrangement of its landmasses. It not only contributed significantly to our knowledge, but also paved the way for the development of more sophisticated scientific frameworks, such as the revolutionary concept of plate tectonics. Q265. Analyze the gaseous hypothesis of Kant in the creation of the universe and Earth. 10 marks, 150 words, core demand of question. Explain the process of gaseous hypothesis. Highlight various limitations of it. OnlyIAS. In 1755, German philosopher Kant introduced the gaseous hypothesis, drawing inspiration from Newton's laws of gravitation and rotatory motion. Kant proposed that stars, akin to planets orbiting the Sun, rotated around the center of the galaxy. This concept revolutionized astronomical thought, shaping our understanding of celestial dynamics. Gaseous hypothesis of Kant in the creation of the universe and Earth. Immanuel Kant, in his book Universal Natural History and Theory of the Heavens, advocated for the nebular hypothesis. He posited that the Sun and planets originated from a primordial cloud of dust and gas. Innumerable particles of primordial matter were scattered in the universe. And these particles started colliding with each other due to gravitational attraction. As a result of this collision, heat was generated. This changed the primordial matter from solid to liquid, and from liquid to a gaseous state. Thus, the original cold and motionless cloud of matter became, in due course, a vast hot nebula and started rotating around its axis, and with a continuous rise in the number of primordial particles, the nebula expanded in size. Due to the continuous increase in the size of the nebula, the speed of rotation became so fast that the centrifugal force exceeded the centripetal force. This created a bulge in the center of the gaseous mass. When this bulge increased in size, the rings started forming one by one and were separated from the middle part of the nebula and were thrown off due to centrifugal force. The residual central mass became the Sun, and the rest of the rings became the planets. However, Kant's hypothesis is plagued by the following limitations. Origin of primordial matter. Kant's hypothesis does not account for the source of the primordial matter from which the universe and celestial bodies originated. It lacks an explanation for how this matter came into existence initially. Energy for particle motion. The hypothesis fails to clarify the source of energy required for the initial random motion of motionless particles, violating Newton's first law of motion, which states that an object at rest remains at rest unless acted upon by an external force. Generation of rotary motion. Kant's theory suggests that collision among primordial matter particles could generate rotary motion without explaining the mechanism for torque generation. This overlooks the necessity of an external force or torque to initiate rotational motion, as per fundamental principles of physics. Contradiction with angular momentum law. The hypothesis proposes that the rotary speed of the nebula increased with its size, contradicting the law of angular momentum conservation, which states that the angular momentum of a system remains constant unless acted upon by an external torque. While Kant's gaseous hypothesis offered intriguing insights into the formation of the universe and Earth, it encounters significant challenges. Its inability to address key aspects like the origin of primordial matter and the source of energy for particle motion underscores its limitations in explaining cosmic origins. Q266. Describe the evolutionary journey of Earth and its atmosphere. Core demand of question. Describe the geological evolution of the Earth. Highlight the development of the Earth's atmosphere. OnlyIAS. In the vast expanse of geological time, Earth and its atmosphere have undergone profound transformations, shaping its dynamic landscape and atmospheric composition. Situated 149 million kilometers from the Sun in the Goldilocks zone, Earth's formation around 4.5 billion years ago from the solar nebula remains a pivotal milestone in its evolutionary journey. The geological evolution of Earth. Formation. Approximately 4.6 billion years ago, Earth coalesced from the solar nebula through accretion, a process where gravity pulled together dust and gas particles, gradually forming the planet we know today. Differentiation. During its formation, Earth underwent differentiation, with denser materials sinking to form the core, composed mainly of iron and nickel, while lighter elements formed the mantle and crust. Volcanic outgassing. Volcanic eruptions were instrumental in shaping Earth's early atmosphere, releasing gases like water vapor, carbon dioxide, nitrogen, methane, and ammonia. This outgassing contributed to the chemical composition of the atmosphere, paving the way for life's emergence. Formation of oceans. As Earth cooled, water vapor in the atmosphere condensed, leading to the formation of oceans. The presence of liquid water on the surface was crucial for the emergence and sustenance of life, making Earth a unique and habitable planet in the solar system. Development of Earth's atmosphere. Photosynthesis. Approximately 3.5 billion years ago, primitive photosynthetic life forms like cyanobacteria emerged. Utilizing sunlight, water, and carbon dioxide, they initiated photosynthesis, steadily augmenting atmospheric oxygen levels. Oxygenation. As oxygen-producing organisms became more abundant, the oxygen they released began to accumulate in the atmosphere. This event, known as the Great Oxygenation Event. Ozone layer. The accumulation of oxygen in the atmosphere led to the formation of the ozone layer. The ozone layer shields the Earth's surface from harmful ultraviolet, UV radiation. Evolution of life. The presence of oxygen and the protection provided by the ozone layer allowed for the diversification and complexity of life on Earth. Over billions of years, life evolved and adapted to different environmental conditions, shaping the Earth's ecosystems. The elucidation of Earth's evolutionary trajectory, alongside its atmospheric development, stands as a testament to humanity's tireless pursuit of knowledge. This comprehensive understanding not only enhances our comprehension of planetary dynamics, but also underscores the profound influence of natural processes on terrestrial evolution. Q267. What are the essential strategies that require sincere adoption to cultivate a comprehensive soil conservation framework in India, effectively balancing the imperatives of food security and ecological equilibrium? 10 marks, 150 words, core demand of question. Provide the essential strategies and measures that India requires to adopt to cultivate a comprehensive soil conservation framework, ensuring food security as well as maintaining ecological equilibrium. ANS. In India, soil erosion has emerged as a critical environmental challenge, having far-reaching consequences on food security, water quality, biodiversity, and overall environmental well-being. With approximately 145 million hectares of reported area requiring urgent conservation measures out of a total of 305.9 million hectares, the need for effective soil conservation strategies becomes evident. Strategies and measures to conserve soil, balancing food security and ecological equilibrium in India. Conservation agriculture. Promote the adoption of reduced tillage, mulching, and cover cropping to minimize soil erosion, ensuring improved crop yields and ecological balance, exemplified by Madhya Pradesh farmers whose practicing conservation agriculture witness increased yields and reduced erosion. Agroforestry promotion. It includes promotion of the integration of trees with crops for stable soil, biodiversity enhancement, and food security. For example, Kerala's home garden agroforestry exemplifies this approach, preserving ecological balance while ensuring food production. Moreover, coffee intercropping with shade trees in Wayanad prevents erosion and conserves soil health. Soil erosion maps and monitoring systems need to be developed to target conservation efforts effectively. For example, Gujarat's Soil Health Card scheme provides farmers soil information for sustainable practices. Additionally, Gujarat's soil erosion maps guide conservation measures in vulnerable areas. Land use regulations and zoning. It should be strictly enforced in ecologically sensitive regions to manage soil erosion sustainably. For example, Uttarakhand's zoning safeguards fragile ecosystems while supporting food security. Also, Uttarakhand's zoning ensures sustainable land use in critical areas. Afforestation and reforestation should be done on degraded lands for soil stabilization, erosion prevention, and carbon sequestration. For example, the Green India Mission balances food security with ecological conservation. Furthermore, afforestation efforts in the Aravalli Hills restore soil health and reduce erosion risks. Terracing and contour farming needs to be adopted on a wider scale to slow water flow, preventing erosion and supporting agriculture. For example, Sikkim's terrace farming achieves food security and ecological balance on challenging terrains by boosting the agricultural output and reducing soil erosion. Integration into policies. Formulate national policies prioritizing soil conservation for sustainable agriculture. For example, the National Mission for Sustainable Agriculture promotes soil health and sustainable practices through incentivization of farmers to adopt conservation practices and promote sustainable agriculture. Agroecological practices. Implement practices in harmony with the environment to improve soil health and reduce erosion risks. For example, Andhra Pradesh's Rithu Siddhikara Sam's that advocates for ecological balance alongside food security, leading to the revitalization of soils and increase in crop productivity. Education and training. It should be provided to the farmers to promote soil conservation techniques for sustainable agriculture. For example, Gujarat's Q264toQ270 empowers farmers to preserve ecological balance and achieve food security through imparting soil conservation knowledge for sustainable practices. Soil testing and nutrient management. Regularly test soil to determine nutrient levels and apply fertilizers judiciously, preventing overuse that can lead to soil degradation. For example, universal application of soil health card. India needs to utilize different strategies or a combination of these strategies depending on the local conditions to address the growing issue of soil erosion. Additionally, the efforts of policymakers, farmers, researchers, and the public need to be unified in the direction of a greener and more sustainable India, where food security and ecological balance can coexist harmoniously. Extra edge: causes of soil erosion in India. Deforestation. Rampant deforestation leads to the removal of vegetation cover, leaving the soil exposed to the erosive forces of wind and water. For example, large-scale deforestation in the Western Ghats and the Himalayas accelerates soil erosion, posing significant challenges to soil conservation efforts. Unsustainable agricultural practices. Intensive agriculture practices, such as excessive plowing, monocropping, and improper irrigation methods, disturb the soil structure and increase erosion rates. In Haryana and Punjab's Green Revolution areas, intensive agriculture practices have contributed to soil degradation and erosion. Overgrazing. Uncontrolled grazing by livestock can lead to the removal of vegetation and the compaction of soil, making it more susceptible to erosion. Overgrazing is a significant concern in arid and semi-arid regions, like Rajasthan's their desert, where soil erosion exacerbates desertification. Improper land use and land cover change. Converting natural landscapes into urban areas or agricultural fields without proper soil conservation measures disrupts the delicate balance, causing increased erosion exemplified by the urban expansion in cities like Delhi and Mumbai. Construction and infrastructure development. Infrastructure projects such as roads, highways, and buildings often result in soil disturbance and loss of vegetation, promoting soil erosion as exemplified by the development of hotels in the Himalayan region to attract tourists. Excessive water erosion. Excessive rainfall and poor water management practices can lead to water erosion, washing away fertile topsoil. The problem is prevalent in regions with heavy monsoons, like the northeastern states and parts of West Bengal. Geographical factors. India's diverse topography, including hilly regions and coastal areas, exacerbates soil erosion. The Himalayan states, the Western Ghats, and the coastal regions experience varying degrees of erosion due to their geographical characteristics. Mining activities. Mining operations, especially open-cast mining, expose vast areas of soil, increasing erosion rates exemplified by the mining belts in Jharkhand and Chhattisgarh. Moreover, climate change, increasing desertification, etc. events are intensifying this process, presenting the urgency to address this issue on a priority basis. Facts and figures. Soil erosion in India occurs at an average annual rate of 16.35 tons per hectare, resulting in a total loss of 5,334 million tons of soil annually. About 29% of the eroded soil is carried away to the sea, and 10% is deposited in reservoirs, leading to a decrease in their storage capacity by 1 to 2% each year. The remaining 61% of eroded soil is displaced from one location to another, contributing to environmental degradation and sedimentation in water bodies. Recent evidence indicates that about 63.85 million hectares, equivalent to 20.17% of the country's total geographical area of 328.72 million hectares, has been transformed into wastelands due to soil erosion and land degradation. Q268. Define seismic retrofitting and explain its importance in making buildings and infrastructure. Earthquake resistant. Provide some examples of successful retrofitting projects in India. 15 marks, 150 words, core demand of question. Define seismic retrofitting and explain its importance in making buildings and infrastructure earthquake resistant. Provide examples of successful retrofitting projects in India. ANS. Seismic retrofitting refers to the process of modifying and strengthening existing buildings, infrastructure, or structures to improve their ability to withstand seismic, earthquake, activity. This involves making structural and non-structural changes to reduce the risk of damage or collapse during an earthquake, thereby enhancing the safety and resilience of the structure and its occupants. Strengthening an old brick building with steel braces and reinforced concrete serves as an example. Importance of seismic retrofitting in making buildings and infrastructure earthquake-resistant. Structural resilience. Seismic retrofitting enhances the structural integrity of buildings and infrastructure, allowing them to withstand seismic forces and ground motion, reducing the risk of structural failure during an earthquake. For example, the retrofitting of San Francisco's Golden Gate Bridge strengthened its ability to withstand earthquakes. Life safety. Retrofitting saves lives by minimizing the risk of building collapses and protecting occupants, making it a critical measure for public safety in earthquake-prone regions. For example, the seismic retrofitting of schools in Japan, which has protected students and staff during earthquakes. Property protection. It safeguards property and investments by reducing structural damage and potential financial losses resulting from earthquake-related destruction. For example, Los Angeles mandated retrofitting vulnerable apartment buildings, thereby preserving affordable housing units, protecting property values, and reducing the risk of displacement following earthquakes. Continuity of critical functions. Retrofitting ensures that essential facilities like hospitals, schools, and emergency response centers remain operational during and after earthquakes, supporting disaster response efforts. For example, hospitals in California have undergone seismic retrofitting to guarantee uninterrupted medical services during earthquakes. Cost-effectiveness. While there is an initial cost associated with retrofitting, it is often more cost-effective than post-earthquake reconstruction, extending the lifespan of existing structures and reducing long-term expenses. For example, retrofitting the Transamerica Pyramid in San Francisco proved more cost-effective than rebuilding the iconic skyscraper from scratch after an earthquake. Community resilience. Seismic retrofitting contributes to the resilience of communities by minimizing disruptions and enabling faster recovery, helping regions bounce back from earthquakes more effectively. For example, this was evident in the rapid recovery of infrastructure and services in Japan following the Great East Japan Earthquake of 2011, thanks to extensive retrofitting efforts. Some examples of successful retrofitting projects in India. Bhuj earthquake reconstruction. After the devastating 2001 earthquake in Bhuj, Gujarat, numerous retrofitting projects were undertaken to strengthen and rebuild damaged structures. These projects included reinforcing buildings with seismic-resistant materials and techniques. Notably, base isolation technology, which uses lead rubber bearings, shock absorbers, to isolate and protect structures during earthquakes, was employed. Ludlow Castle School retrofit in Delhi. This project implemented a prescriptive system of micro-concrete seismic belts, in accordance with Indian building codes. The initiative also included comprehensive awareness programs, evacuation plans, and preparedness drills. This school now stands as a national and local model for earthquake safety. Delhi Divisional Commissioner's Office Buildings Retrofit. The retrofit of 2 concrete office buildings at the Delhi Divisional Commissioner's Office Complex in Delhi utilized reinforced concrete shear walls to enhance their seismic resistance. Delhi Police Headquarters Retrofit. This project combined the incorporation of new shear walls with modifications to existing walls, fortifying the building's earthquake resilience. Delhi Secretariat Retrofit. In this case, columns were wrapped to augment their ability to deform during an earthquake, significantly bolstering the building's seismic performance. Guru Tegh Bahadur Hospital Retrofit in Delhi. The retrofit of this hospital focused on anchoring interior brick partition walls and equipment, substantially increasing the facility's earthquake resistance. Seismic retrofitting stands as a crucial process in fortifying the earthquake resilience of buildings and infrastructure. By prioritizing seismic retrofitting today, we can not only safeguard lives and assets, but also lay the foundation for a safer and more resilient future for generations to come. Q269. Discuss the concept of virtual water and its pertinence in the strategic management of water resources within India's intricate drainage system. 10M Core Demand of Question. Provide the key components of virtual water. Describe the pertinence of virtual water in the strategic management of water resources within India's intricate drainage system. ANS. Virtual water refers to the concealed water used in the production of commodities and services, which are subsequently traded or consumed. It embodies the water quantity entailed in the complete production cycle of an item, encompassing crop cultivation, manufacturing, and transportation. For example, the water employed in cultivating and processing coffee beans, subsequently exported and utilized in another nation. Components of virtual water. Primary production water. This component refers to the direct water used in the cultivation of agricultural products, such as crops and livestock. It includes rainwater and irrigation water needed to grow plants and raise animals. For example, in India, irrigation consumes about 84% of total available water. Secondary production water. Also known as industrial water, this component represents the water used in the manufacturing and processing of goods. It covers the water required for processing, cleaning, cooling, and other industrial processes. For example, industrial sector consume about 13% of total available water. Processing and packaging water. This component includes the water used in processing, packaging, and preparing products for distribution and consumption. It encompasses activities like cleaning, sorting, packaging, and labeling. Transportation water. Water is used indirectly in the transportation of goods from production sites to markets. This includes the water consumed in various transportation modes such as trucks, ships, trains, and planes. Distribution water. This component accounts for the water used in distributing products to retail outlets and consumers. It includes activities like warehousing, refrigeration, and retail operations. Consumption water. The final component reflects the water needed to consume or use a product. For example, the water used to brew coffee, wash clothes, or cook food after purchasing goods. Pertinence of virtual water in the strategic management of water resources within India's intricate drainage system. Water-efficient trade. By comprehending the virtual water content of exports like rice, cotton, and sugar, India can strategically shift from water-intensive crops to less demanding ones, optimizing water use. For example, Punjab and Haryana, significant rice producers, could transition some rice cultivation to less water-intensive crops such as pulses, promoting sustainable agriculture. Import and export decisions. Virtual water guides water-intensive import decisions. High virtual water content suggests imports over domestic production, relieving water-stressed regions. For example, India's soybean oil imports from Brazil exemplify efficient water use due to virtual water awareness. Water footprint of industry. Industries carry substantial virtual water footprints from manufacturing's water consumption. Assessment of product virtual water content empowers policymakers to promote water-efficient practices, attracting region-compatible industries. For example, Tamil Nadu's Tirupur textile sector embraced eco-friendly dyeing, reducing water use, a testament to virtual water's role in sustainable industry. Interstate water sharing. Virtual water analysis can aid just interstate water sharing. Surplus states can prioritize high virtual water content crops, while deficit states can opt for less water-intensive ones, promoting efficient allocation and reducing disputes. For example, the Kaveri dispute between Karnataka and Tamil Nadu underscores virtual water's role in equitable allocation and crop selection. Urbanization and food demand. Virtual water content is beneficial in urban planning and agricultural policies for promoting sustainable food production amid urbanization. Urban gardening and rooftop farming of vegetables with low virtual water content can help enhance food security. For example, vertical farming, which involves cultivating water-efficient crops like leafy greens, showcases the role of virtual water in achieving urban sustainability. To conclude, the paradigm of virtual water offers a transformative avenue for India's water resource management. By harnessing this concept innovatively through smart agricultural shifts, leveraging global trade dynamics, promoting water-savvy industries, fostering collaborative interstate agreements, and integrating urban farming initiatives, India can pave the path for a future where water scarcity is mitigated, ecological equilibrium is restored, and a harmonious coexistence with our intricate drainage system is realized. Extra edge. The amount of virtual water in a product can vary greatly. For example, it takes about 1,000 liters of water to produce a kilogram of beef, but only about 250 liters of water to produce a kilogram of wheat. Based on research published in the Groundwater for Sustainable Development Journal covering the period of 2006-2016, India annually exported approximately 26,000 million liters of virtual water. The primary exports included rice, buffalo meat, and maize. With minimal virtual water exports prior to 1990, India's virtual water exports have surged to reach 32 billion cubic meters during the span from 1990 to 2018. Q270. Investigate the promising prospects offered by soil biotechnology and microbial-mediated mechanisms in bolstering soil health and revitalizing degraded lands within the context of India. 10 marks, 150 words, core demand of question. Explain the promising aspects offered by soil biotechnology and microbial-mediated mechanisms in bolstering soil health and revitalizing degraded lands within the context of India. Provide the associated challenges. Suggest some innovative solutions through a way forward. OnlyIAS. Soil biotechnology refers to the application of biological techniques, including the use of microorganisms, plants, and organic materials, to improve soil health, fertility, and overall ecosystem functions, while microbe-mediated mechanisms focus on the vital roles of microorganisms, such as bacteria and fungi, in nutrient cycling and soil ecosystem functioning. Promising aspects of soil biotechnology and microbial-mediated mechanisms in bolstering soil health and rehabilitating degraded landscapes in India. Enhanced nutrient availability. Soil biotechnology can enhance nutrient availability through the microbial processes. For example, the use of nitrogen-fixing bacteria can improve soil fertility, as seen in legume crop rotations in India. Biocontrol of pathogens. Microorganisms can act as natural biocontrol agents against soil-borne pathogens, for example. Trichoderma species have been employed to suppress diseases in crops like tomatoes and cucumbers. Organic matter decomposition. Soil biotechnology accelerates organic matter decomposition, releasing nutrients. For example, earthworms used in vermicomposting contribute to this process and enrich soil structure. Restoration of soil structure. Microbes play a role in soil aggregation, aiding water infiltration and root penetration. For example, mycorrhizal fungi like glomus form symbiotic relationships with plants, improving soil structure. Phytoremediation. Certain plants, with the help of soil microorganisms, can remove contaminants from the soil. For example, sunflower plants have been used to clean up heavy metal-contaminated soils. Increased drought resistance. Microbial inoculants can improve water use efficiency in crops, enhancing drought resistance. For example, Azospirillum bacteria, when applied to cereals, can enhance water stress tolerance. Reduced soil erosion. Plant growth-promoting bacteria can stimulate root development, reducing soil erosion. For example, rhizobacteria like Pseudomonas fluorescens have shown potential in stabilizing soil against erosion. Carbon sequestration. Soil microorganisms contribute to carbon sequestration, mitigating climate change. For example, agroforestry systems with nitrogen-fixing trees, such as acacia and casuarina, enhance carbon storage. Biodegradation of pollutants. Microbes can break down organic pollutants in soil. For example, oil-degrading bacteria, like Pseudomonas and Bacillus species, aid in the bioremediation of oil-contaminated sites. Soil agroecosystem resilience. Microbial diversity enhances soil agroecosystem resilience. Crop rotations and intercropping in India encourage diverse microbial communities, contributing to pest management and disease suppression. Nutrient cycling and nutrient retention. Microbes participate in nutrient cycling, benefiting agriculture. For example, phosphorus-solubilizing bacteria increase phosphorus availability to plants, impacting crop yields. Similarly, application of biochar, a type of charcoal produced from organic waste materials, improves water retention, nutrient retention, and microbial activity in the soil. Conversion of agricultural residues. Microbes aid in converting agricultural residues into valuable resources. For example, decomposing fungi, such as trichoderma, are used in composting to convert crop residues into nutrient-rich compost. Rehabilitating degraded lands. Microbes help restore degraded lands. Biofertilizers and biochar promote plant growth on barren lands. For example, Greening India program, which uses microbial technology for reforestation and land restoration. Resilience to climate change. Soil microbes enhance soil structure, aiding water retention and resistance to erosion, crucial in adapting to changing climates. Adapting traditional practices. Ancient practices like Jivamrit in India involve microbial preparations for soil fertility, demonstrating the indigenous knowledge of soil biotechnology. Associated challenges. Microbial diversity and composition. Understanding and maintaining diverse microbial communities is essential for soil health. For example, monoculture farming can lead to reduced microbial diversity, impacting nutrient cycling and plant health. Environmental stressors. External factors like pollution, climate change, and pesticide use can disrupt soil microbial communities. Excessive pesticide use in cotton farming has been linked to negative impacts on soil microbial populations, reducing their ability to support healthy plant growth. Soil degradation. Degraded soils with low organic matter and poor structure limit microbial activity. For instance, overgrazing in India's grasslands reduces soil organic matter, impacting microbial diversity and soil health. Limited knowledge and research. The complex interactions among soil microorganisms are not fully understood. For example, despite the importance of arbuscular mycorrhizal fungi in enhancing plant nutrient uptake, there is still limited research on their specific interactions with different crops in various Indian agroecosystems. Application techniques. Effective delivery of microbial inoculants to soil can be challenging. Inconsistent application may limit their beneficial effects. For instance, improper inoculation methods can reduce the effectiveness of beneficial soil bacteria. Socioeconomic factors. Socioeconomic constraints, such as limited access to resources and technology, can hinder the adoption of microbial-based soil management practices. Small-scale farmers in rural India may face challenges in accessing and affording microbial products. Regulatory and policy frameworks. Still lack of clear regulations and policies for microbial products in agriculture can hinder their adoption. For example, the absence of standardized testing and certification processes for microbial products can create uncertainty among farmers about their quality and efficacy. Way forward. Microbial consortia development. Collaborative research and public-private partnerships, as seen in the United States Microbiome Initiative, can foster the development of diverse microbial consortia tailored to India's agroecosystems. Precision microbial application. Utilizing precision agriculture technologies, such as sensor-based systems and drones, can enable targeted application of microbial products, optimizing their efficacy and minimizing wastage, similar to Japan's use of drones for precision spraying. Microbial seed coatings. Employing microbial-coated seeds, inspired by Australia's smart seeder technology, can ensure efficient and uniform distribution of beneficial microorganisms during planting, enhancing crop establishment and early growth. Digital soil health monitoring. Developing digital platforms and mobile apps for real-time monitoring of soil health, akin to Africa's AFSGS project, can provide farmers in India with actionable insights to make informed decisions on microbial interventions. Community-led microbial projects. Encouraging community participation and knowledge sharing, as demonstrated by Brazil's Microbial Bioprospection Program, can empower Indian farmers to co-develop and implement microbial-based solutions for local challenges. Microbial data banks. Establishing centralized microbial data banks, akin to Europe's microbiome data warehouse, can facilitate the cataloging of diverse microbial species and their functions, aiding researchers and practitioners in informed decision-making. Microbial entrepreneurship. Fostering a culture of microbial entrepreneurship, similar to Israel's innovation ecosystem, can encourage startups and enterprises to develop novel microbial